So,
He said that last week.
so big hints on this. It tells you it's an SN1 mechanism, and as soon as you see SN1, you should immediately. All of that, I think, is too difficult. Make a carbocation.
There it is.
The electrons leave the carbon, go to the iodine, and we would produce our product, where we have the positive charge and officially the iodide.
Do you have to write it every time because it's an inorganic? Or?
The iodide, no, I would immediately stop drawing it, but I figured someone was going to complain. I want to address something about this because I noticed a couple people doing this. That is the correct structure. What is that?
Not the correct structure.
What's different? You added an extra carbon. Be very careful. The positive charge just sits next to a point. If you add an extra line, you're showing an extra carbon. Okay? So that's our carbocation. Okay? Once we have the carbocation, we have two options. We can either do the substitution route or the elimination route. Okay? We have both options because both the SN1 and the E1 do the exact same first step. Well, which route should I do? Substitution, because it says do the substitution. Okay? So for the substitution, I need a source of electrons to stabilize that positive charge. The iodide left, it doesn't make sense to have it come back, so I could go through and show the other source of electrons being our water and having it come in and stabilize, and we'd start our substitution. Before you look outside a structure, though, you must look within. It was a deep pause, and it really came out a little more zen than I wanted it to. Right. And this is the other hint given to you at the top. We form a carbocation, it's SN1, and rearrangement. We have to do a rearrangement. Well, we don't have to, but we're given a big hint that we should do one. Okay? I noticed a lot of people saying, okay, well, there's electrons. I immediately got to shuttle them over because I'm in a rush. Got to do it. Okay? The result of that would be, for those of you copying this, you might hold off on copying, would be that structure. What is the difference between my two structures? Nothing. Okay? So that was not a particularly useful rearrangement. Okay? For those people that have been attending the tutoring center, one of the big common issues that I've been seeing pop up is particularly when we move into the elimination. Okay? And in the elimination, what's the big problem? What are we doing in an elimination reaction? Okay? I hear a lot of people typically say the formation of a pi bond. When we talked about it earlier. We said the formation of a pi bond is a bad signifier as far as trying to predict a mechanism. For looking at a reaction, does a pi bond show up? Sure, that's an elimination, but not useful in doing a mechanism. Okay? In doing the mechanism, only two things happen in an elimination. We break the leaving group and we break a carbon-hydrogen bond. Why is the hydrogen causing so many problems? It's implied. Guess what the issue is with this structure? There's an implied hydrogen. One of the, good point, one of those implied hydrogens results in the formation of this carbocation. That is now a more stable carbocation because it's tertiary versus secondary. The rearrangement occurs. Okay? Because I found a source of electrons within the structure, that happens first. It is always, can't get too philosophical on that one. It is easier to fix your own problems than to have somebody fix them for you. Right? That wasn't too bad. Yes. Say that again?
Why is that hydrogen specifically used?
Okay. What about the blue hydrogen? It's too far away. Okay, I can only do short distances. Ultimately, just a 1-2 difference. Okay. So what about the green hydrogen? Same issue, too far away. What about the black hydrogen? The black hydrogen is actually close enough to do the rearrangement. What happens if it rearranges? I form a primary carbocation that's less stable. That means that rearrangement's not going to happen. Okay. Now that I have a stable carbocation, now I can continue on with the rest of the reaction with the substitution and define a source of electrons. This is where water with its lone pairs can come in and share. The result is now a positive oxygen. This is more stable than the carbocation because octet rule. Okay. Is that a stable final product? No, because it's charged. So what has to happen? We have to lose a hydrogen. So if we add our curved arrows, we would end up with, gosh, I'm drawing that ugly. It is kind of a person flipping over a table. In any case, we now have our alcohol, our final substitution product. A couple issues may pop up here. How did the hydrogen just leave the structure? Hydrogens can come on and off the structure pretty much at will, okay, as long as they're acidic. This would be acidic because we're forming a stable oxygen at the end of this. A lot of people don't like just having hydrogen come on and off a structure and so have to show something pick it up. What would need to pick up that hydrogen? A base, okay? Except I'm not in a basic environment. So really what I need is just a source of electrons. Where do I have electrons? There's a second equivalent of water. There's also iodide, which is the better structure to show pick up the electron. Why is water the better source of electrons than the iodide? If iodide picks up the hydrogen, we form HI. What is special about HI? It's by definition a strong acid. If water picks it up, it's H3O+. H3O+ is not by definition a strong acid. Okay? It's actually a weaker acid. We'll always form the weaker acid. Okay? So depending on how the question is formatted, you may want to show the H3O+, you may not. The way the textbook showed this is they showed two equivalents of water because they wanted to show the water picking up that extra equivalent. Okay? But that's it. You don't have to. And we've now done a substitution with a carbocation rearrangement. When do we need to worry about rearrangements? Every time you find a carbocation, which happens in SN1s, it also happens in E1s. It can happen in additions. Okay? Carbocations can happen virtually anywhere. We have to be careful. Anytime we see one, we should consider a rearrangement. Okay? There's our answer. SN2, our repercussions. What was the big issue with our SN2? It is one step, so the iodide comes in and attacks. Where does the iodide come in and attack?
Backside attack.
It's a backside attack. Thanks for fixing. Yeah, and you ruined it. So close. Let's just walk away from that. Sure hope that didn't get recorded. I'm not going to edit any videos. That is way too much effort. And we'd end up with the iodide now on the back side because the chloride was on the front originally. And we've done our substitution reaction. Okay. As it's drawn, it's not easy to see the inversion. We attempted to go through and show this earlier, and I did it with my hands and said, yeah, we could break my hands and we could see that that happened. And that's not a particularly fun thing to do. Your textbook has gone through and showed an umbrella effect, doing much the same idea. The iodide comes in from the back side. If those blue atoms are our umbrella cover, and the chloride is where the point is, when the iodide comes in, it then causes the umbrella to flip the other direction. Okay? So they're just showing that inversion in the stereochemistry. It does not always mean we get inversion. Okay? The only reason it is inversion is because we are losing a high priority group and we're adding a high priority group. If the other atoms are also high priority, we then have to reevaluate, and it may not necessarily be an inversion in stereochemistry. It is an inversion of the arrangement of the atoms, not necessarily stereochemistry. Yes?
So iodide is a more stable anion than chloride. Why is this?
So here's an interesting concept. What are you asking here?
My
If I
question
push
is,
it again.
why is the reaction happening? Because iodide is more stable than chloride.
Does everybody catch what's happening here? This is an equilibrium reaction. Chloride could just as easily come in and attack and kick out the iodide. So why are we favoring the iodide product and not the chloride product? If it's bigger, it is then more stable, and I should expect iodide to be chilling on its own because it's more stable. This comes down to a definition of what's happening with our nucleophiles. Size does affect this in a couple ways. It does make the negative charge more stable, but it also makes it more polarizable. A good nucleophile is highly polarizable. Iodide turns out to be a better nucleophile than chloride. Size does contribute. That size effect really plays a role when we look at the solvent, and that's one of the later things that we'll look at in Chapter 9. The reaction does favor the formation of the iodide in this case, or the alkyl iodide, as opposed to the alkyl chloride. Okay? Because the iodide is a better nucleophile, even though it appears to be more stable. Okay? It's a tricky concept, one that thankfully you don't have to deal with all that often. Okay? Which then gets us into our elimination. Would have been nice if that was stepwise, so let's kind of make it stepwise. When we do the E1, the repercussion that we talked about earlier was that we have the potential for cis and trans products. And it's all coming down to how the E1 reaction works. In the E1, what is the first step? The leaving group leaves. Right? The 1 means the same thing, whether it's elimination or substitution. The 2 means the same thing, whether it's elimination or substitution. Right? So our leaving group leaves, and we form a carbocation. To form the pi bond, what now has to happen? What has to happen? What sigma bond has to break? A carbon-hydrogen bond has to break. I have to take the electrons in that bond and move them into a pi bond. So I end up losing that hydrogen. The result is H plus floats off on its own. Okay? All right, so well, why is that a big deal? Why are we even referencing that? Well, the instant the electrons come in to form the pi bond, what then happens or becomes characteristic of that bond? It can't rotate, which means the arrangement of the groups that are attached to the atoms of the pi bond are now locked into position, which is why we have the potential for cis or trans. In the E1, we have a carbocation, which means where can the electrons go? To form that pi bond, the electrons can come either to the top or the bottom. In the orientation shown, the electrons are coming in from the top. Prior to the pi bond formation, what could I do about that now purple bond? I can do the action shown in red, which is a rotation. I could rotate it such that the hydrogen is aimed downwards with respect to the carbocation, so that my electrons could come in from the bottom. If I do that, what happens to the arrangement of that ring and the methyl? They change their location. Okay? That means when I do the final elimination, I get 2 possible results. Whoa, come back here. That is,
Super embarrassing.
stop it. That is what your textbook is trying to show. In the top case, what they're attempting to show is the electrons coming in from the top. In the bottom case, they're coming in from the bottom. The end result is that I end up either with the large groups on opposite sides of the double bond, so I have a trans, or I end up with the large groups on the same side, or cis. Okay. Because this is all happening in solution, I get the choice. Both of those are possible options. Which option would I predict to see in a larger amount? The trans, because it's more stable. It's a lower energy structure. Okay? And because the elimination reaction is endothermic, okay, we start with our energy diagram. We've got our reactant. We're going to form our product. We're just going to do the elimination. Stuff happens. Don't worry about it. And then product, it's an endothermic reaction. It goes up in energy. Okay? If I have two possible options, which option do I want? I want the lower energy one, because what's going to happen to the peaks of all that stuff that's I said to ignore? It's going to drop significantly because it's an endothermic reaction. That was our whole Hammond postulate. The transition state is closer in energy to whichever one is closer to it. Since it's an endothermic reaction, the transition state is dependent on the energy of our products. If our products are different in energy, the transition state is going to drop for the lower energy one. That one happens first. Okay? So when we run the elimination, or the E1 elimination, we tend to see just the trans. I find this orientation of the figures a little bit confusing. So what I went through and tried to do was show the p orbital. Okay? And so if we look at the top situation, those electrons from our hydrogen, and actually let's ignore that. If we don't do a rotation, the electrons can come directly into the p orbital, which then means the phenyl group was dashed and the other phenyl group was wedged, which means I don't accept cis and trans. I would only get the trans according to that orientation. What happens if after I form that carbocation I get a sigma bond rotation? Okay. Now the hydrogen's oriented on the bottom. The result is the methyl and the phenyl have now changed their relative position to the other phenyl. When I do that next elimination, what happens? Now I have the phenyl coming out and the other phenyl coming out. They're on the same side and cis. Okay? So I end up with the cis product versus the trans. You'll notice that I initially drew these with wedges and dashes. Why did I initially draw them with wedges and dashes? To better accent the orientation of our drawing. Okay. Is it correct to show wedges and dashes on a carbon that is sp2 hybridized? No. Why not? When do we show wedges and dashes? Chiral atoms. When do we have a chiral atom? 4 different things attached to it. Okay? An sp2 atom does not have 4 different things. So it is not a good idea to show it that way. We would redraw the structure to give us the trigonal planar geometry. Notice in the trigonal planar, I'm trying to make sure I have 120 degrees between each of those bonds. And I am not, say, showing this result, okay, which is relevant for the homework. Which one's cis, which one's trans now, according to the structure shown at the bottom? Who the hell knows? You haven't established that in a way that it's actually interpretable, which then means the computer, okay, which is worse than a human at interpreting things, really has no clue of what you're trying to draw and marks you wrong, because there's now no difference between those. Okay? The only way we can establish our difference is if we fully accent where our atoms are located. Show the proper bondings. Okay? You won't lose points, at least on an exam, as long as it's obvious what's happening within it. Okay? Sometimes it is, sometimes it isn't. Kind of make sense? Okay. So when we run the elimination, or the E1 elimination mechanism, more than likely we end up with the trans product. We can still get the cis, we just don't get it in as high a yield. Okay? It ends up being the minor product, or a minor contributor. Make sense? So if that's the E1, what's going to happen with the E2?
Same thing, but faster.
So same thing but faster. Speed is irrelevant. Do not bring speed into this. Okay? Which mechanism goes faster, E1 or E2? It depends on a variety of other external factors that we have no control over. Don't bring speed into it. Okay? And you can't even look at the number of steps. There could be a 20-step reaction that goes faster than a one-step reaction. Okay? So you can't bring speed in based off the number of steps.
Well, I think you're saying the difference between is like one has multiple steps, one doesn't.
Intermediates.
I think I see where you're going.
That's what I mean.
Okay. Since we're talking about stability, if we ran this reaction, we get two products, right? We get the cis or the trans.
Yes.
Everybody see that? Okay. To do the elimination, what did we do? Okay, we broke the leaving group bond. What else did we do? We broke a carbon-hydrogen. Where's that carbon-hydrogen? On the neighboring carbon, right? So we broke that hydrogen off. Okay, so let's get through some nomenclature on this. The leaving group is attached to the first carbon. Okay? But it's not really the first carbon. It's actually the second carbon as far as nomenclature goes. So I don't want to call it first. I'll use a different numbering system. That's weird. We don't have a numerical system other than numbers. Like letters, maybe? The first letter of the alphabet? A. So if you said A, that's number 1. Okay? But A is too confusing, so we can bring in Greek letters. And that first position where our leaving group is located is the alpha position. Where's the hydrogen located? At the beta position. And one of the names associated with an elimination reaction is not just calling it an elimination, but it's calling it a beta elimination, because we are eliminating a group from the beta position. Okay? So you might hear reference to that. Sometimes that's helpful, sometimes that's not. Okay? Why am I bringing it up now? How many beta positions are there? What is that blue atom? It is a neighboring carbon. And if alpha is number 1, what is that blue carbon if I count that direction? I also have another beta position, which means
You gotta determine which beta is correct.
right idea. What are we looking at? So if we're trying to decide which beta is correct, we need to evaluate the stability of the products. So maybe we should draw the product of that elimination. What does it look like?
It's 2 on the far right.
Did we lose any carbons? No.
We lost the hydrogen.
We lost the hydrogen where?
Disappeared into a
Our blue beta position, which became negative. What did our leaving group do? Left, making that carbon positive. What is our product? Okay. Here we go. That's another product. Okay. So in running this elimination, I don't get 2 products, I get 3 products. So what does that mean?
You gotta choose the most stable.
I got to choose the most stable of those 3 products. Which is the most stable of those 3 products?
Top right.
Okay, the top right, our trans was more stable than the cis. Because resonance is not the answer. It's a steric repulsion. It's those methyl groups pushing away from each other. Okay? If we move to the bottom one, is there any steric repulsion? There's only one group. There can't be any steric repulsion. So does that make that one better?
Yes,
Unfortunately, no. What makes our pi bond reactive? The electrons. Those electrons really have 3 directions in which they can leave the structure. When we look at the trans, how many directions can they leave the structure? Only 2. The methyl groups are sources of electrons. You can imagine them as effectively blocking the electron density from leaving the pi bond, which then means which structure is more stable, the trans or our terminal? The trans. Which is more stable, having electrons internally or externally? Internally. When we're looking at stability, it's all about, do the electrons go into the structure? If the electrons are embedded in the structure, what can they not do? React. Okay? So which is our more stable? The trans. Okay? So it's all based off of the stability of double bonds. And you might say, well, didn't we talk about that? Yeah, we did. We did talk about the stability of our double bonds. And it's all looking at that stabilization. Okay? Strictly, we can't use that hand-wavy electrons moving around. Okay? It goes back to the Hammond postulate. Our transition state is closer in energy to our product because it's an endothermic reaction. Okay? That's why we see the trans forming over the other 2. How do we establish that that one is more stable? Oh, God. Go away. That would be this slide, which we had before. Tetra-substituted is more stable than tri-substituted, more stable than di-substituted, more stable than mono-substituted. Okay? So that is our double bond substitution patterns. We saw this when we looked at the heat of combustion in chapter 3, I think. Okay. So it's coming back again in predicting which product we get. We will always make the more stable product. That's what this energy diagram is trying to go through and show. All of these are going through the same intermediate, that carbocation, and they all go through to form the final product. Because it's an endothermic reaction, I drew that kind of ugly. Jeez. Someone is massively salty today. You're a little briny. I like that one better.
Good one.
Okay. Our endothermic reactions, okay, our transition state is closest in energy to our endothermic. That means we get a significant difference in our transition states. The lower energy our product, or the more stable our double bond, more likely to form. So which one was our lowest energy? B, the next one. A, then C. So we look at our substitution patterns first, then we can evaluate cis and trans. Okay? We've got a new one popping up, heat of hydration. What is heat of hydration? The heat necessary to add hydrogen, okay, to saturate the structure, because currently all of these are unsaturated because of the double bond. That's what that red thing at the bottom is representing, the fully saturated structure. Which of those compounds have the largest heat of hydration? C, because it's the biggest gap between the energy of C and the fully saturated version. The more stable your structure, the smaller the heat of hydration. Okay. What type of reaction would a hydration reaction be? It's an addition. We're adding hydrogen across the double bond. Have we talked about addition reactions yet? No. Guess what the next unit is? Addition, where we will talk about the addition of hydrogen. Okay. So The more substituted your double bond, the more stable. Okay? Which then comes along, all those stupid circles. Actually, that's kind of important because people are messing that up. That first one is tetrasubstituted. Okay? If I look at just a standard alkene, okay, that is my bare minimum alkene. Simplest I can get. If we're now saying it is substituted, what are we doing? We're removing a hydrogen. We are required to have 4 different things attached to an alkene because octet. Okay? So when we're referencing the substitution, what we're saying is I got rid of a hydrogen and I made it something else. That is literally the answer. Okay? Typically we're referencing just some other kind of carbon. It does not have to be a CH3. It can be really anything. It could be any kind of R group. So a tetrasubstituted means all of those hydrogens have been replaced with something other than hydrogen. Trisubstituted?
3 of them.
3 have been replaced. Monosubstituted? 1. Oh, didn't fall for that trick. Okay? So, if an elimination reaction occurs, if given a choice, you need to produce the most stable elimination product, the most stable alkene. Okay? The major product is the more substituted double bond. This is typically credited to uber dead Russian guy, Zaitsev, with a variety of different spellings of his name, because nobody can spell Russian stuff. Okay? His rule is not actually the major product is the more substituted double bond. His rule is that when you do the elimination, the hydrogen you remove comes from the carbon that has the fewest hydrogens. You mean you form the most stable double bond? Yes. Yes, that's exactly it. But why could he not evaluate stability? Why did he have to reference the hydrogen? Zaitsev existed before we knew electrons existed. He made this observation based solely off of the products, had no idea about electrons or protons. Right? So his theory is based off of hydrogens, not based off of the stability of the double bond. So why are we still talking about Zaitsev? Why don't we just say form a more stable double bond? Because that's a pretty cool observation to make when you didn't know that there were electrons and protons. Okay? So his name gets attached to it, and everybody then forever remembers, oh, it's a Zaitsev rule thing. Make the most stable double bond. That's the point of an elimination. Unfortunately, as you might notice in small font at the bottom of this, we do have an exception. Right? The exception does get a name. Why? Well, because almost everything follows Zaitsev. The instant we find some weird case where it doesn't follow it, they get to attach their name to it. The person that did it, Hoffman. Okay? So in very particular circumstances, if the hydrogen is sterically hindered, okay, and we use a sterically hindered base, then and only then will we get the less substituted double bond, or really the least substituted double bond. Right? We're using a base. When is a base relevant? In the E1 or the E2? You can cheat because the answer's up there.
E2.
E2. Okay? The base is being used to remove the hydrogen in the E2. Why do we not care about a base in the E1? Do I not need to break a hydrogen? I do. It's not the slow step in the E1, because in the E1, I break the leaving group. And that's the one I'm concerned about. I'm not concerned about the carbon hydrogen. In the E2, it's all happening at the same instant, so now I'm concerned about breaking that hydrogen off. That's why the base comes in the E2 and the E2 only. Which leads kind of nicely into our E2 reaction. What is our repercussion for the E2? What is the difference between the two structures shown?
The font size of OH.
The benzene. That benzene space.
and the dash on the right side one.
Okay, wedges and dashes, is that it? So that you're saying that that's the difference? Which means the relationship between those structures is? Why are you saying diastereomers and not enantiomers? Didn't it mirror?
No.
This position mirrored, didn't it?
Yep. Sure did.
Did the other one?
No.
No, it did not. It stayed exactly the same. If it stays the same, they are not enantiomers, they are diastereomers. Okay? And those of you being like, I don't even remember having to do with that. Sorry, that's chirality. Comes back to haunt you again. Okay? In the E2, everything happens at the exact same instant, so the leaving group leaves. And the base comes in and removes the hydrogen. Because it's all happening at the exact same instant, I have one step, which means I can now evaluate the rate for this reaction. The rate for this reaction will be dependent on what? The base and the substrate. Two things, that's why we call it E2, or second order. Okay. What is the product that I would expect to get out of that one? An alkene, good. And two phenols. I'm just going to write them as pH. We're going to do it this way. Why am I doing it that way? Can you tell where the pHs are relative to each other? In my drawing, no. The starting material dictates the orientation of those pHs. What should those pHs be relative to each other? Why should they be trans? One is shown as a wedge. The other one is shown as a dash, which by definition means they're on opposite sides of the pi bond as it forms, which means we get the trans product. What happens with the rest of this? Well, the methyl is out there. What happens with the bottom one? Same thing, except now we have cis. Well, couldn't I just like rotate? I mean, we did it with the, what was the other thing? The SN2. Can't I just rotate, put the bromine up here, and then get the trans? Why does that not work? What is the hydroxide? Whoops, as I erase it again. A base. What is that base supplying? Electrons. So those electrons are coming in. What is the bromide doing? With electrons. What happens when those electrons get near other electrons? They repel away, and the base can't do the elimination. So that orientation shown down below doesn't work. The one above does. What is the difference between those orientations? It's all the relative orientation of the leaving group and the hydrogen being removed. And as Wyatt, I think, just pointed out, what's the name? You don't remember what it was? It looked like you mouthed it, so I could be wrong. The top one is anti. What's happening in the bottom one? It's actually eclipsed, which is really problematic because not only is the eclipse not stable, it's so not stable it never exists. If we go back to our Newman projections with the energy diagrams, where do we see the eclipsed? It's a peak. It never exists. It's a transition state, which means I can't do an elimination from there because it doesn't exist. Right? So when I run the E2 elimination, I have to make sure that the hydrogen that I'm removing and the leaving group are anti to each other. If they are not anti, nothing happens. Right? Couple things come out of this. Number one, we get one product when we run an elimination. Right? We don't get a mix of products which we could have gotten. Oh, I need the next thing. Which we could have gotten with the E1. We favored the trans, but we usually end up with some cis. In the E2, we only get one product. Hey, how many products do we get in the SN2? One. Interesting. E1, SN1, E2, SN2. We get lots of parallels running between those reactions because they're ultimately doing the same thing at different locations. Right? So I can end up getting the trans product. I can also get the cis product, and that is going to be determined based off of the starting material I'm working with. Let's bring speed into it. Which of these reactions would I expect to react faster, form products faster, the top one or the bottom one? Why the top one?
The bottom one doesn't even occur.
Careful. The bottom one absolutely has the proper orientation to do the elimination. The product is more stable in the top one than in the bottom one. I would expect a higher yield and at faster rates for the top one because I form a more stable product. The bottom one can still occur. That structure isn't wrong, and I can still do that elimination because I have the anti-alignment. The issue is that that product is now so much higher in energy that the likelihood of making it in decent yields is pretty crappy. Okay? Make sense? Yes?
How come we didn't, so we could say hydrogen and bromine are anti, but they're not anti in terms of like wedged and dashed, right? They're both lines.
How do we show anti?
There's no pi bond, so you can't say that there's.
When did anti as a word come up? Newman projections. Guess what you need to do? You need to draw a Newman projection. And in the process of drawing out the Newman projection, you can see that alignment. Okay? The anti-configuration that you're probably used to, I'm just clearing up some space in that corner. What is the relationship between A and B? They're on opposite sides, so they're anti. That's the one that everybody sees. What is the relationship between C and D? They're also anti. Right? If I turned and looked at this structure from the side, there's A, there's B. Everybody agree with that? So I took that front carbon and just pulled it to the left. Where's C? It's on the right-hand side. Should it be wedged or dashed? Should be wedged. We're taking that front carbon, which is really hard for me, and I drew it nice and high so I can't point to it. I'm taking that front carbon and I'm pulling it this direction. Which then means where is C aimed? At you, which is wedged. Where did D go? Dashed away. So where can you see anti? A and B tend to be really easy, drawn in the plane, one's aimed up, one's aimed down. Right? You also get anti off axis or off the plane wedges and dashes. Right? Which is easier for you to see? That's up to you. I personally think the solid lines A and B are easier to see than C and D being anti. Okay? And that comes with practice. Okay? So there's our Newman projections to show the alignment. We have to have the anti-alignment to do the elimination. If we do any other alignment, what ends up happening is the hydrogen and the bromine end up forming in a gauche arrangement at best. When the base comes in, it sees the bromine and gets repulsed away. Can't form that product. We move to the other gauche situation, right? We'll run into the exact same issue. Right? This means that we have to have our hydrogen and our leaving group what is known as anti-configuration, and why on the Earth do we decide to change the word? We do. It is typically referenced as anti-periplanar when we're looking at elimination reactions instead of the anti-configuration. Okay, so you may see that word pop up. All it's referring to is anti. Why is this not a problem for the E1?
It's just the leaving group, please.
In the E1, the leaving group's left, which leaves behind.
No need to go through the back.
Yeah, I can accept that. No steric hindrance. Right? Which means the base can come in and remove the hydrogen from any angle. It's completely irrelevant because there's nothing now blocking it. Take it a step further. The electrons from that hydrogen bond are going into what orbital? A p orbital. With a carbocation, we have a p orbital, and that p orbital is occupied above and below the plane, so it doesn't matter where the hydrogen is, either above or below, because it can always swoop into one of those empty lobes of our p orbital. Okay? So we don't have to worry about it. Can we still get mixtures from the E2? Yes. Why can we get a mixture from the E2 in this case, but not in the other cases? The leaving group has to leave, and I have to remove a hydrogen from the beta position. Alpha, beta, what's at the beta position? 2 hydrogens, which means either one can be removed to do the elimination. That will show or produce 2 different products, one being trans and one being cis. So I get a mixture of products in that case. Why was that not an issue with the previous one? There's our leaving group at the alpha position. At our beta position, how many hydrogens do we have? Only 1. That's why I don't have an issue initially. The instant I add more hydrogens, I can get more products. So, Chapter 8. What Chapter 8 is asking you to do is, given that the information is SN1, E1, E2, or SN2, then predict the product. Okay? You might even have to add curved arrows. Okay? Within those circumstances, to predict those products, what do you need to take into consideration? Well, the E2, we need to have anti-alignment. The E1, what did we have to consider? Well, that's probably far enough back. What did we need for the E1? Form the more stable double bond. Right? The most substituted. Okay, so what we're doing is just looking at the complications of each of these reactions. That's what Chapter 8 does. It says this is substitution of a SN1 variety. This is the result that comes out of it. Oh, look at all this crap that goes sideways. Remember that crap. This is an SN2 reaction. What's the repercussion of an SN2 reaction? Well, I get inversion in stereochemistry. Remember that. Okay? Draw that when it shows up. That's what you're doing in Chapter 8. Okay? What happens when we move into Chapter 9? That's supposed to be an eraser. What's the product? You have to make it. What do you need to analyze to decide what the product is? Okay. Structure of the substrate is going to come in handy. We could look at the solvent. That'll come in handy. Am I given a nucleophile? As soon as I see a nucleophile, what should I be saying? Substitution. Okay? Leaving group is our other thing to consider. Okay? In eliminations, we don't have a nucleophile. We typically have a base. So by looking at the reagents, you can now say, oh, that means that's an elimination. That means that's a substitution. So what you have to do is evaluate all of the pieces, add them up, and say, the sum total of all the information given to me says that I do an SN1 reaction. The sum total of all that information means I do an E2 elimination or an E2 reaction. Okay? That's Chapter 9. You are now attempting to predict things based off the context of the information given to you. That means you have to evaluate each of the pieces behind those mechanisms of those reactions and see how changes to those affect which type of mechanism. Okay? I gave you a precursor to this, which I would love to say was on the next slide, but it's not. Yep, it's really not. Okay? There was that table. Right? It said SN1, SN2, E1, E2 across the top, and then it said substrate, nucleophile, and listed, I think, 5 things down the other side. What you're using is that table to interpret. Okay? If you have a substrate that favors an SN1, you check the SN1. Okay? Then you check the nucleophile, you check the base. Okay? And you decide, based off of that, which mechanism you're running. Then what do?
Then you do it.
Then you do it. Now you look at your answers, and you've got your answer for your multiple choice. Okay? So, considerations that we have to remember from Chapter 8. Carbocations. The instant you see a carbocation, you need to think rearrangements. Where do carbocations show up? SN1, E1. 1 means carbocation. Okay? Acid-base steps, leveling effects. Okay? Kind of a weird one, so don't stress a whole lot. If you're in a strongly basic environment, what should you never make? Strong acids. Okay? If you're in a strongly acidic environment, don't ever make a strong base. Okay? And then intramolecular reactions, which we haven't talked about yet. Okay? Typically, you want to avoid intramolecular reactions because they are very rare, and you typically get forced into them. Okay? What does intramolecular mean? Within the structure. Okay? So I've dumped those slides to the very end because I wanted to get through some content stuff. So on our substitution elimination, this summarizes virtually everything you could see. You've got your substrate, your leaving group, your nucleophile and or base, and your solvent. Okay? The substrate contains the electrophilic carbon. That electrophilic carbon could be sp2, zeroary, primary, secondary, tertiary, or allylic. Those of us that are in lab, tell me what allylic means. Oh, he remembers the monkeys throwing food. Nice. There's a double bond nearby, which allows for resonance. Okay? So we have to look for resonance effects with our substrate. Your leaving group, it's the atom that takes electrons from the carbon structure. The easiest examples are bromine and chlorine, okay, or bromide and chloride. Are other atoms good potential leaving groups? Yeah, like what? Oh, I see what you're saying. Iodide, yes. Those of us in lab on Monday have the answer to the question, what other atom could potentially act as a leaving group? What other atom could act as a leaving group? What is a characteristic of bromide, chloride, and iodide? Size, yes. That's actually going to be misleading. They're all electronegative. Fluoride doesn't work so well because super, super tiny. But oxygen is electronegative and can quickly be stabilized by adding on a hydrogen, allowing for resonance. So oxygen can also be used as a leaving group under special circumstances. The next thing is looking at the nucleophile and the base. What is the difference between a nucleophile and a base? Good question. We'll address that when we move further on through the chapters. Solvent, that's the solution that facilitates or hurts the reaction. When deciding on your solvent, it's really going to come down to, yep, that helped, or oh crap, that hurts. If it hurts, don't use it. Okay? If it helps, that's the one you want to use. Okay? So typically when we're looking at it, it's the kind of giving you an answer here. Protic solvents are used for the SN1. Aprotic are used for the SN2. The protic solvent helps the SN1. A protic solvent hurts SN2. A nonpolar solvent hurts SN2. There's only 3 solvent classes. If 2 of them hurt, what are you left with? The last one, which is polar aprotic. Okay? So we've got some answers already put in on this slide. So So all of that information is in slides. What I want to draw your attention to, sorry if people were watching this at home and just got sick, is at the very, very end, we have some summary slides. For an SN1, our substrate, we want a stable carbocation. That's what dictates it. Leaving group should be good. Okay? Nucleophile, it's weak and or irrelevant for the SN1. Okay? These are all things we've already addressed and talked about. They just haven't been explicitly summarized. So I want to draw your attention to those slides, even though I'm going to double back here in a second, because you should be using those slides to answer questions in Chapter 9. Because you're using that information to say, oh, the substrate is tertiary. And a tertiary substrate does what for me? Stabilizes what? Carbocations, which would suggest which mechanism? SN1. So it's looking at that bit of information and then applying it out. Right? So now we'll get sick the other direction. Thanks for the musical interlude.
Do you have a picture of spine versus spine on one of those slides?
Maybe. Our substrate classifications. We have zeroary, primary, secondary, tertiary, which we already saw when we looked at our carbocations. When we look at alkyl halides, we'll look at the carbon where the halogen's attached. So in that top case, the bromine's attached to a carbon. How many carbons connected to that carbon? 0. So that alkyl halide is referred to as a zeroary alkyl halide. Okay? So it's coming up with a quick substrate classification. The bottom one? Tertiary, because the carbon where my chemistry will occur has 3 carbons connected. Right? When we're looking at our SN1, we're concerned about the stability of a carbocation. So which substrate would I want to use? One that produces a tertiary carbocation. So a tertiary halide is awesome for an SN1. Okay? A zeroary is horrible. It is in fact so horrible that if you see a zeroary alkyl halide, it does not exist in the SN1 mechanism. If you have the potential for a primary to form, doesn't exist. Which means to run an SN1 reaction, I must have a secondary or better carbocation. What's better than secondary? What's better than tertiary? Quaternary doesn't exist. You can't have that many bonds. Say that again? Resonance. Classify that carbocation for me. It's secondary, so the carbon that's holding the carbocation is connected to 2 other carbons. It is primary plus resonance. Resonance is too long of a word, doesn't sound cool enough, so we call it primary allylic. It's primary, so should that react in an SN1 mechanism? No. But because it's resonance, it does. Where does it react? Faster than our tertiary. Okay? Resonance trumps the inductive effect that we're getting from our other carbons. Okay? When we move to the SN2, should I be looking at the carbocation? No. So if I'm looking at my substrates, for the SN2, which of those would I expect to react the fastest? So 0, 1, 2, 3. 3, I'm hearing, should react the fastest. What happens in the SN2? Nolan? This is your jam. SN2. What happens in the SN2? It's our backside attack. What's the issue on the backside of the tertiary? What's back there? Carbons. What do carbons have? Electrons. Can the tertiary substrate react under SN2 conditions? No. If you have a tertiary substrate, no SN2. Okay? Doesn't happen. So secondary, primary, zero area. Which one would we expect to react fastest under the SN2? The zero area, because it has the least hindrance. Okay? What's the issue with addressing the secondary? It's small enough that it does react. Let's push that further. Where else did the secondary react? SN1. What does that mean? If you have a secondary substrate, both SN1 and SN2 are possible options. We cannot eliminate our choice based on the substrate. So what do we have to do? Come on. We move to not leaving group. Dang, what is wrong with the order of this? We move to, frick, nucleophiles. Okay, sorry the order was a little bit messed up. Okay. Why substrate to nucleophiles? Substrates are relatively easy to interpret. Nucleophiles, relatively easy to interpret. Solvents suck. Leaving groups, they all need a leaving group, so who cares? Okay? So what we're trying to do is look at those classifications and see how they affect our overall reaction based off the mechanism information we already have. I would highly, again, recommend that you go back and watch the small videos that I posted about each of those sections so that when we pick up Monday, we can finish off talking about some simple stuff, look at review, and then just do review questions. Ideally the practice exam or even smart work questions.